Hi, everyone. Thank you to Alon for introducing me and to all of you for being here. My name is Santos, and I'll be presenting on, as she said, MultiWindow Shiny, a package to connect Shiny applications across multiple windows. So as you all likely know, since you're here, Shiny is a great package for our users that lets them develop interactive web applications without the need for learning web development languages, such as HTML and CSS. In R, Shiny apps are structured through the UI and server functionality, where the UI variable contains the front-end user-facing functionality and inputs, and the server function takes user input and renders output accordingly. This creates interesting, malleable interfaces that can make a variety of topics accessible, including population dynamics, transportation routes, and even movies. Despite the variety of topics, all the examples I just showed you have one thing in common. They span only one window. And when you have a lot of inputs and outputs, this can get quite crowded and ever more confusing. You can alleviate this slightly by adding separate tabs, but in that way, it's difficult to compare outputs directly. Further, we are increasingly living in a multi-monitor world. So how many of you have at least 2 monitors at your workstation? Yeah, a fair amount of you. So we propose to take advantage of that, letting Shiny apps be connected across multiple monitors. Another situation we can think of is an external controller directing inputs for a visualization-focused monitor. So how do we actually address this problem? We use MultiWindow Shiny. mwshiny, or MultiWindow Shiny, extends the Shiny across multiple windows, extending the interface easily. It uses Shiny's familiar syntax and conventions, so it's pretty easy to pick up for anyone who's already learned Shiny. MultiWindow Shiny does this by breaking out app development into 3 parts: user interface development, server computation, and server output. Our multi-window environment begins by specifying the user interface for each of the windows. That is what the user sees on each window. And this is done through window titles and user interface arguments. These are win titles, a vector of strings specifying the name of each window, and UI win, a list that contains the traditional Shiny UIs corresponding to each title. In this example, we have 2 windows called controller and scatter. And when we run our multi-window Shiny app, we see that window on the top right where you can actually choose which window corresponds to each. Then we define the user interfaces for each of the corresponding windows, at first for what we call the controller and the next for the scatter window. Next, we move on to what we call our server calculations, where we observe events and create variables for output to be rendered. This is a list of functions of the form function calc_sess, where calc is a reactive variable that contains all the Shiny input variables, as well as a place to put any derived variables we use in output, and sess, which is just the traditional Shiny server session variable. In this example, we observe when our input go changes, and then create our data frame accordingly, adding it to our calc variable. We then finally come to our server output, which is a named list of functions in the same previous form, which returns a render result corresponding to the output ID. So in this example, we render our scatter plot based on our calculated data frame and return that in our function. After you have all these 3 pieces, you then pass them into the mwsapp function, along with the stated JavaScript and CSS dependencies, and it runs your multi-window Shiny app. By separating the traditional server section into computation and output, we force increased clarity of workflow, breaking computation down into manageable, smaller chunks. This is also enhanced by the function and list structure of serveout and servecalc, which also encourage code chunkiness. In order to demonstrate the efficacy of MultiWindow Shiny and its workflow, we want to show 3 case studies: multiple monitors at a workstation, a controller driving an external monitor, and an alternative visualization structure. So we first look at the first case study, a simple 2-monitor situation to visualize population dynamics. Using the 2010 US Census of the continental US, we want to compare overall levels of various statistics to specific statistics at both a state and a county level. We start with the first stage of our workflow, which is defining our user interface. In this case, I want 2 windows, which I call controller and map. The first user interface specifies user inputs, as well as several density plots, while the other simply shows the map colored by the chosen statistic. Now that I've determined what I want my users to see, I have to actually calculate what I need for my visualizations based on this input. I added an action button to generate my input so that I only wanted to generate visualizations when the user actually specifies. I'm not going to go too into the weeds on this. If you want to check out the code for all of these examples, it's at my GitHub at that link on the bottom. But I do this through my calculate function, which only contains our observe event function to trigger on the button click. When that happens, we add data frames to our calculus to be used by various plot renders. After we've calculated based on inputs, we can render 3 different objects: a density plot based on the aggregate of all the states together, a density plot comparing the county level data of our selected states, and a map colored by our specific statistic. Once we put all these parts together, we end up with our double monitor Shiny app, where we can compare the discrete statistics for each state on the map with the overall trends in the density plots. MultiWindow Shiny allows us to easily take advantage of our expanded screen real estate to make comparisons between large plots on the fly without being compressed to one screen. So now that we've shown a basic 2-monitor situation, we move on to the next 2-monitor situation, a controller driving an external monitor. Though these largely show the same setup, the goal is very different from the workspace monitor situation. So to illustrate this example, we look at the case of someone seeking to learn more about their favorite artists in a museum. Information is displayed on an external monitor for the user, and the user has access to either a separate tablet in front of the monitor or their own phone where they can make choices. As with any multi-window Shiny workflow, we start with defining our user interface. It's very similar to the last with 2 windows. However, the large difference comes from the way we want to set up each of these UIs. Our controller window has exclusively user inputs, while our art monitor has exclusively output. Since the purpose of this app is largely to display information, our computation section is relatively small. However, here it's really important to note that in this computation, we're also allowing the user to choose what they see with the update tab set panel function every time they want to see something new. And this allows for no need for interaction directly through the monitor. On the output side, however, we have a lot of different information to render based on the artist and the aspect the user wants to see, including the artist's birthplace and some representative paintings. Once we put all the pieces together, we end up with our ideal monitor control situation where a separate controller window controls the output for our monitor window, showing the artist information and representative pictures of our example artist, Van Gogh. Thus, in this way, our Shiny can be used to power controller-driven applications for any variety of topics. For our last case study, we'll move on to something completely different, a multi-window Shiny to work on an alternative visualization method, the Rensselaer Campfire, which was developed at my school, RPI. The campfire, which is a cylindrical 3D structure, consists of a circular floor and a rectangular wall wrapping around the floor. When we break this down, we can see the 2 monitors creating the campfire more clearly, a circle and a rectangle. Since the campfire structure handles all window warping, all we have to do is think about is dealing with these 2 monitors. We also have access to a controller to initialize visualization. Users can surround and interact with the campfire to explore their data. And by using this 3D structure, we increase collaboration and enhance innovation. We also reduce cognitive load. That is, by having the ability to see data in a 3D fashion, it becomes easier to compare disparate sets of data. So using the campfire, we're going to examine something that impacts the health of all of us, circadian rhythms. Circadian rhythms are roughly 24-hour cycles that are reinforced by external light cues. In data from organisms such as mice, they look like cyclic cosine waves that can change amplitude over time, which we can categorize based on that amplitude change. When we interrupt these rhythms, it can lead to an increased risk of many health problems, such as cancer and diabetes. And once we identify these rhythms, we want to know what their function is and how they interact with each other within their amplitude changing categories in the hopes of isolating root causes of dysfunction. This application is based on the Encore methodology, which you can find on GitHub. As always, we begin with what we want our user interface to look like. In this case, we have 3 windows to manage. Our simple controller, where we select gene function where we want, and our floor and wall. The floor is simply going to display a chord diagram of interacting genes, and the wall will have a heat map of what our expression looked like over time with each gene. Once we have our user interfaces in order, we can develop our calculations based on that input. Once a user selected a gene function, we create the data for the chord diagram and the heat map. Since we have the ability to have mouse interaction in the Campfire, we also have other calculations to trigger on hovering on different chords, which change the visualization in the Campfire accordingly. And we've added these observations as separate calculations in the computation section. After we've made all these calculations, we simply render our output in our serve out list, with the wall showing our heat map for each gene, with the yellow as high expression and the blue as low expression, and our floor showing the interaction presence between each gene sets. So once we put all our pieces together from our workflow, we can see in our example for the function metabolic process in the Campfire. We can also hover on specific genes to focus on their connections so that we can figure out which genes are more highly connected or influencing other genes. For example, we've hovered on RPS 11, which has 11 gene connections, more than many of the genes represented. So users can continue to explore genes in this way, collaborating to discover ever more information through this 3D structure. So just as a quick summary of what we've talked about, we introduced the package mwshiny, which extends standard Shiny to have multiple windows. And we developed a workflow for these multi-window Shiny apps, which increased clarity. We then presented 3 different simple case studies in 3 different fields: a multi-monitor system illustrating population dynamics, a controller driving situation increasing cultural awareness, and an alternative visualization in the Campfire illustrating the impact of circadian rhythms on gene function. These case studies show the impact of multi-window Shiny as we move into a future with ever more immersive applications and structures. So I would like to thank the Hurley Lab for all their support and feedback, and the Ideal Lab, including Kristen Bennett, my advisor, and John Erickson, who helped me work on this project in the Campfire. This work is supported by the NSF, RPI, and the NIH. Thank you all very much for listening.